Welcome back to Computer Science 252 at the University of Wisconsin, Eau Claire. This will be mini lecture number 4, and we'll talk about device files and a little bit more. Before we begin, I'd like to challenge you to think carefully about each of the following lines in Bash. See if you can figure out see if you understand what they mean. If you do, awesome. And I want you to try to do it on your own. Open up a terminal with Bash and see if you were right. If you're not sure, I'd encourage you to go back to the last two mini lectures and a little bit lab number 7 and see if you can figure out what they mean. And again, once you figure it out, try it. And pause before going on. In Linux, all the files and directories on the entire system are located underneath the root directory in a tree-like structure. The directories that are directly underneath the root directory, man, that sounds crazy, are listed here. Now these may vary a little bit depending on the version of Linux, but these are generally the ones that you'll see. /bin is a directory that contains a lot of commands like bash, grep, and other things, usually pre-installed programs. /boot contains information about how to boot the system. /dev contains device files, which are kind of like drivers. We'll talk about those today. /etc contains a bunch of settings for the system. /home contains like user directories. And we won't really talk about many of these right now, but the very bottom one, /proc, is another one that we'll talk about briefly in this lecture. Linux treats lots of operations like files. This is just part of the Linux philosophy. So, for instance, if you want to write a message to the standard output stream, you can treat it like writing to a file, and we've seen that. fprintf, standard out, and then whatever message you would use just as if you were using printf. So you're treating it as if you're writing to a file called standard out. Easy enough. But you can also read and write to devices too. So for instance, if you want to read input from the mouse, treat it like reading from a file, the mouse file. If you want to send output to the internet, treat it like writing to the internet file. Now it's more complicated, there's a bunch of them for the internet, but you can treat it like writing to the internet file. If you want to generate a bunch of random numbers, treat it like reading from a file that just gives you a continuous stream of random numbers. Easy peasy. Device files are inherently related to device drivers. You're probably familiar with drivers. They're software that control or drive a specific device on a computer. So you've got like sound card drivers, you've got a video card driver, you've got a driver for your screen, you've got a driver for your USB ports, and so on and so on. In Linux, a device file is the interface by which you communicate with the device driver. If you output something to the device file, then the driver is going to read that and communicate that to the device. If you read from a device file, you're going to be getting information from that device. So device files allow us to communicate with devices, physical devices, via standard I/O, which is pretty cool. And of course, since these special device files are connected to these devices and drivers in some special way, they don't behave quite like ordinary files. If I'm reading from the mouse file, it's a little different than if I'm reading from other kinds of files. Examples of device files. So one is /dev/HDA. This is the master IDA drive. So this is related to your hard drive. /dev/SDA is also related to the hard drive. So this is a SCSI hard disk with the lowest SCSI ID. If you have more than one SCSI hard disk, it can be SDA-A, SDA-B, SDA, SDB, SDC, and so on. And same for HDA, HDB, HDC. Now, if you have multiple partitions on a given hard disk, say your SCSI hard disk, then SDA1 is the first partition on the hard disk SDA. SDA2 is the second partition on on the first hard drive. You can have SDB1, and that's the first partition on the second hard drive, and so on and so on. So they've got a cool naming scheme. Now, for historical posterity purposes, there's also FD0, which is the floppy drive. And if you're lucky enough to have more than one floppy drive, then you can have /dev/FD1 at /dev/FD2, and so on. On some systems, there are the exact names for some of these devices are a little bit obfuscated. It's a little unclear and confusing. So they've made some nicer, easier to understand names for some of these devices. For instance, /dev/cd-rom. It's a link to the cd-rom device file. Now the cd-rom device file is actually called other things in different flavors of Linux, but a lot of systems use this just as a nice shortcut. And /dev/mouse. The mouse is a complicated device. It works more based on events, but you can connect to it using this if your system has this alias. There are also things called pseudo-device files. Now, a pseudo-device file is like a device file, but its behavior is even weirder than regular device files in some ways. So /dev/random or /dev/urandom are two device files where if you read from those files, they just return an endless stream of random numbers. So you could use these random numbers to initialize variables or an array for a simulation or for cryptography or so on. /dev/random is higher cryptographically secure, better quality random numbers. Urandom is more faster, lower quality random numbers. /dev/null is probably the most popular and most in the public eye in terms of the pseudo-device files. If you pipe anything to here or you redirect any IO to /dev/null, then that output will disappear. So anything that you write to this file just disappears. It's like a black hole, it's a void. So if you want to ignore, say, standard output from your program, you could redirect your standard output from your program on the command line to /dev/null, and you won't see that output anymore. /dev/0. This is kind of like /dev/random in that if you read from that file, it just returns an endless stream of zeros. Now, there's faster, more efficient ways of initializing your arrays to 0 in C, but if you want to do this, say, in the command line or something like that, or if you need to pass in an endless stream of zeros to a program for some reason, you could, just by redirecting this as your standard input stream into a command. Process files are related to device files in some ways. We'll talk more about threads and processes later, but I wanted to introduce some things. Here are some examples of process files. /pros/devices lists all registered character and block devices, which are different kinds of device files, and other things. /proc/CPU info gives you some information about the CPU if you want to know how many cores does my computer have. You can look there. /proc/uptime tells you how long the system has been online, so if you want to know when was the last time I restarted, you could find out from there. If you want to know what version of Linux you're running, you could go to /proc/version, and that has information all about the Linux kernel version. Let's have some fun. You're already familiar with three device files: standard out, standard air, and standard in. And these are actually located in /dev as standard in, standard out, and standard air. Cool. Now you might think, I could have some fun with this. I'm going to create a program that outputs, "I'm the best programmer ever." And you compile it and you run it and you redirect the output to /dev/standard air. And you're like, hey, I get to see this. And you run it and sure enough, it redirects to standard air. Cool. But then you're like, I'm going to bring this to the thing servers and I'm going to run it and it's going to output to everybody's standard air all at once. So if I redirect it then to /dev/standard air on the thing servers, then maybe it will pop up, I'm the greatest programmer ever on everybody's standard air, everyone who's logged in. And sadly, the answer is no. And the reason for this is actually kind of interesting. Whenever you create a new, whenever you log into the thing servers, you create a new process for bash. And so this terminal, when you create it and when you run bash, it's going to have its own copy of standard out, standard air, and standard in. And those are going to actually be located under proc/self and then /fd for device files. So /proc/self refers to the current process that's running, your terminal session, not everybody else's. Therefore, when you redirect your output from your program to /dev/standard air, it's only an alias that points to standard air for your current session, not for everybody's session. Here are some review questions, so I encourage you to pause here and see if you can answer all of these. What is a device file? What is the philosophy behind treating devices like files? Why does Linux do it like it does? And what is /dev/null and how can you use it? For the first of two practice problems, I want you to write a C program that outputs both standard out and standard error. Now, you did this in lab number 7, so you could just reuse that program. That's fine. For the second part of this problem is compile and run the program, but use bash's IO redirection to ignore standard error. Now to do that, you want to redirect standard error to /dev/null. That way, your standard error will be obliterated by the black hole that is /dev/null, and only standard error or standard out will print to the screen. For the second practice problem, I want you to write a C program that asks the user for values from standard in to initialize a 20-element array. So loop over the array 20 times, initializing each of the elements, asking the user for input each time. After that, print all of the array elements. Okay, pretty easy, right? 10 minutes. Number 2, compile and run the program, but use bash's IO redirection to take as your input /dev/zeros. So instead of the user typing in a whole bunch of values for the 20 elements of the array, now we're going to have /dev/zeros fill those in. So all of those elements in the array should be 0. Then when you print the array elements, you can test and see, did they really end up being 0? So that's practice problem number 2, and that's the end of this lecture. I hope you enjoyed, and I hope to hear from you soon. Take care. Jess out.